discussed briefly yesterday. Yesterday we were talking really about what is learning and what we need to prevent as AI experts in the future in terms of like do not create too high expectations or unreasonable expectation from the public. But that's very hard because of, as we discussed, there's a lot of misinformation out there, but even other things that are not necessarily negative, like science fiction, that make people think that we already achieve the emulation of intelligence. So we discuss about how statistics are good for many things, but when it comes to AI, then we need to be a bit more careful. We also discuss about what could be coming next beyond large language models, and we said that in the future we want to see LLMs that are more grounded into some sort of fact checking or in a sort of system one, system two. We'll discuss this more in the final lecture tomorrow. And then once again, we highlighted that the goal of a large language model is to create human sounding text. It's mostly trained for plausibility to give you a plausible answer. There is no cognitive architecture. The system does not visualize things like we normally do when we are telling each other's stories, narratives, or even like what we did during the day. And last but not least, it's still just a language model. So it's not like it does things for you just yet. Now, many people are already working on embedding large language models in some more practical applications, but we're still far from seeing that mainstream. Then another big question was how to define intelligence once again. And these are discussions that dates back to the Chinese room argument. So am I just happy to consider something intelligence just because I give an input and I get a reasonable output, or do I also want to look inside and see how the reasoning is done? So we also highlighted the fact that language is just a standard, and that's why we should come up with some sort of universal representation that can help us perform reasoning in a computational manner, just rather than just playing with conditional probabilities and co-occurrence frequencies. And there's still a lot to do, as we discussed. The brain is still the most amazing thing in the universe in terms of not just what it can do, but also how efficiently it can do it. And we're still very far from that. Even the best systems, as we discuss, they are not truly intelligent. They're mostly expert systems, and sometimes to emulate even just part of the brain, we need maybe like a room full of servers, and the brain can do that without consuming that much energy or occupying so much space. We also talked about what is the role of AI in the future and important questions about how we should engineer the future of AI. And of course, I don't have the answer to these questions, but in our little corner, we wrote this manifesto about 2 years ago, which once again serves more as a call for participation to work on some topics that we consider important for the future of AI. So we discussed about each of these yesterday. Then before concluding, there were also quite a lot of questions on how important these pillars are and how can they be implemented in different contexts. So that's pretty much where we stopped yesterday. And today I just want to zoom in into the pillar of task decomposition. So task decomposition, once again, is about breaking a more complex task into simpler tasks. This is nothing new, but we kind of lost this habit of doing things in a modular way because now we have these very powerful transformers, these models that we can just throw as much data as we can, throw as much hardware at it as we can, and then we get good results, and we don't care exactly how these results are produced. So in this sort of paradigm of NLU framework, we are taking a step back and say, okay, it's okay to use large language models, but then if you really want to use them, you need to also, first of all, you should also look at other techniques like knowledge graphs and semantic network. But even if you want to take a purely statistical approach, you should at least have some modules that use those statistical algorithms to perform all these different tasks. Why? Because if I don't take care of these tasks, if I don't do training for it, yes, there will be some emergent features, but still, it's very unlikely that my system can do things the way I expect. And it's not just about that. We'll talk about later. There are at least 10 more reasons for why we want to use this framework. But before I go there, I want to clarify these two terms. So once again, a slide about terminology. NLP, as you know, is natural language processing. We explained also yesterday what it means, natural language. And a subset of natural language processing is natural language understanding. Language understanding, which is also in the title of my recent books, try to go one step beyond NLP. So NLP can be something as simple as, once again, counting word occurrences and to perform a simple classification task, even like a task that is considered kind of complex, like sentiment analysis, can be done in an NLP manner. Why? Because you can build an algorithm that is as simple as having a list of positive keywords, negative keywords, and use that to do the binary classification. But actually, if you want to look in depth into sentiment analysis, then there are so many more things to look at. Look at having like an emotion categorization model, understanding what emotions are and how to use them to produce a polarity, taking into account also different stances or like intention awareness, personality, a presence of sarcasm. So it's not too much about the application. So in this slide, there are a lot of examples that make you think that NLP is for some applications and NLU is for some other applications, but actually it's not like that, because again, sentiment analysis can be achieved either by using NLP or NLU. It's more about how deep you want to go into the analysis, how fine-grained your analysis is, and whether you want to try to really achieve understanding. So in an NLP settings for sentiment analysis, you only care about the accuracy and the output, basically positive and negative. In an NLU case, instead, you want to see, for example, what are the emotions detected, what are the causes of these emotions, and how these emotion cause pairs contribute to the polarity. So it's also one step forward towards explainability and interpretability of the system. So there's not really clear distinction between these two, but the biggest difference is exactly that. In NLP, in the case of NLP, you're just happy to have a statistical model that gives you a high accuracy. In NLU case, you want to build models that are possibly cognitive inspired, that also work on meaning and do more finer grained analysis. So the curse or blessing of NLU is that everything is interrelated. There are so many tasks like the one that we'll talk next, and it can be a bit complicated, but also it's very attractive because again, to do these properly, we also need to look at neurosciences. As we discussed yesterday, we need to understand how the brain works if we want to create a model that is truly intelligent. But once again, we can just focus on a specific domain to make it feasible. So, and this is something that we also discussed yesterday when we talk about symbol grounding. Doing symbol grounding for all possible concepts and all possible languages is probably impossible. But if you focus yourself on a specific domain specific task like sentiment analysis, then things become more feasible. And it also very much depends on what you're doing with NLP or NLU. So if you're just doing an assignment for or information retrieval assignment or assignment for this course, it's okay to have around 80% accuracy quality. And if you're doing PhD, maybe 85, but when you go work in a company, a 90 plus percent accuracy is required. So let's go and look at this suitcase model more in detail. I believe you have seen already some of these modules in the tutorials, but still I'm going to go through these one by one. But before we start looking at each module one by one, I want to clarify that the reason for using this model is that we want to increase accuracy, but the accuracy is not the main focus here, because probably when you talk about accuracy, it's better to just have a large language model, train it on all the possible data that I have, and in a sense, hope that all these tasks that we're going to see next will be automatically emerging from the training data. But if you take an approach that is more modular like this, in which you could potentially even have an LLM for each of these tasks, then you have a lot of benefits that are not necessarily in terms of accuracy, but definitely more interpretability, because then if you can study what is the output of each of these modules, then you can understand, for example, if you have an error, when it's time to do error analysis, it would be maybe much easier to do in this kind of settings, but also explainability, because then if you ask the system how it came to that specific conclusion, it can go through this sort of chain of thought. This is also something that today is very popular among AI researchers. Instead of just using an LLM blindly to blurb out a response, you force the LLM to go through some specific steps, reasoning steps. That's called chain of thought. And then you can all do this also in parallel. That's when you have trees of thoughts. We can talk about that later if you are interested. But the main goal here is to have something modular that can be more interpretable, that can be more explainable, potentially also reducing hallucination, again, because I am forcing the system to go through some specified steps. Easier to perform updates, because then I don't have to retrain the whole large language model, but I can do just a small update on the modules that required. So also streamline evaluation, more fine-grained evaluation, so that I know exactly how each module is contributing to the final output. And this also allows me, for example, to do an ablation study, which is not something that you can do on an LLM. It's supposedly also more scalable, cognitive inspired. It allows for parallel development, because then if I have many people working on this framework, I can have an expert for each of these 15 different modules, instead of having 15 people trying to work out together on the same project. Supposedly it's also more robust, because again, you are looking at the problem in a fine-grained manner. And finally, supposedly also more reliable, because mostly because of the higher interpretability and enhanced explainability. Anyway, I'm happy to discuss about this later. I'm also welcoming people that do not agree with this kind of approach, and that they may prefer to just use an LLM to do natural language understanding. But nonetheless, I want to go through these modules quite quickly. Today's lecture is really only about this, and many of you probably already know all these, but still want to go through this because I think it's important for you to know what each of these NLP tasks are about. And once again, here I'm not saying that you have to do these for any downstream task. It depends on what your task is and what is your domain and what is your training data. If, for example, in your training data there is no sarcasm, then you can skip this module. If you don't have pronouns, you can probably do not do enough resolution and so on. It really much depends on what you're working with. For us, here the downstream task for my group would be sentiment analysis or affective computing. And this doesn't mean that we stop there. Then, as I mentioned yesterday, on top of this, I can also do other things, like, for example, performing depression detection based on polarity detection and emotion detection as well. So again, this is meant as a general chart for you to take into consideration and to implement some of it. So it's divided into three layers because the first layer is working mostly at the syntactic level. That's more about NLP kind of analysis. Next, we have a semantic layer where we look at some tasks that require a bit of more of a semantic awareness, and finally pragmatics, where we look at even more complex tasks that require also having some external models or sometimes external knowledge base to perform things properly. So the first module is a microtext normalization. And here you also have many more details about all these modules in the textbook. So for those of you who are maybe doing a PhD on any of these or have some people working on it, you can have more details in the book. In the book, we talk about the current state of the art for each of these NLP tasks, at least until last year. And we also provide data set, benchmark, all the things you need to get started with any of these tasks. And usually my PhD students, they do either some of them either focus on just one of these tasks, and some of them they do two or more. But then, yeah, depending on how much you want to go into details, each of these modules can potentially be a PhD. So again, here in this next few slides, I'm just going to quickly go through each of these modules. But for those who are actually very interested in this or are doing a PhD on this, please take a look at the book. You have syntactics processing on chapter 2, then you have semantics processing in chapter 3, and finally pragmatics processing in chapter 4. So this is another overview of the syntactics layer where we have 5 modules, and for each of them also we have listed some technical trends. So the first is microtext normalization. What is microtext? We also mentioned this briefly in the past few days. It depends on what kind of data you're working with. If you're working with, let's say, legal documents or financial reports, you don't care about microtext. But if you're working with social media, which is very can be very useful even for financial forecasting, you need to have a microtext normalization tool that normalizes microtext or informal text into proper words for which you can have like a dictionary in an information retrieval setting, or maybe some embeddings. You could potentially also build embeddings that match these microtext, but it's better to have, once again, sort of cognitive inspire approach that tells you that, for example, a sequence like this where you have L08 and R, you could have a very simple approach where you have this stored in a Python dictionary and replace it every time you see this, but then it's very static. You wouldn't be able to catch all these microtext forms. It would be better to have some sort of algorithm that maybe shift to the phonetics domain and translate this into later based on the phonetics. And that's exactly what we have done for some of our works. Even we have a version of SentiGNet called Phone SentiGNet where we do this so that we can catch all those misspellings or different inflections of verbs and nouns and adjectives that we have in SentiGNet. So this goes back to the discussion that we had about the fact that text is actually sound. So sound, speech, communication, vocal communication came before written communication, and it can be tricky because many of the sounds, even like you take words like write, like something that it's write, and write like writing on a piece of paper, they have very similar sound, if not exactly the same sound, but then depending on the context we can disambiguate. And here on the right you have a funny comics that shows how the same sound can actually mean so many different things in different contexts. And this is also very much applicable to some languages where you don't have a specific formal written form. It's Hokkien or Singlish is an example for this, where people very much know what an ang pao is. But then if you ask them to write it down, there's not like just one way to write it, because there's not, it's not really like a formal language, Singlish. So in that case, you can write Ang Pao in so many different ways. And here there are some possible spelling permutations. So how do you deal with the language like that? And this is also what's happening now on social media with microtext. People come up with all sorts of not just acronyms and emoji and emoticons, but also all sorts of different ways of pronouncing English words. So the simplest approach, once again, would be to have a dictionary, like a Python dictionary, that have all these entries and replace them with maybe the most canonical form, Ang Pao. But the best way to do this would be to actually have an algorithm that can shift to the phonetic domain, like using the International Phonetic Alphabet or other simpler tools like Soundex, which is a very simple algorithm, but it can still be useful in some contexts, to shift to the phonetic domain and then try to connect each of these spelling permutation to the one in your knowledge base or in your list of embeddings that sounds like it. Of course, you don't have to do this all the time, but only in those cases where you don't have enough matches of the words that you're working with. And here in the next slides, I put also some other types of normalizations that are very similar to microtext. One is when you have to deal with British versus American English, and that's also a big problem because then you don't want to have too many duplicates in your concept lists. You maybe want to have your dictionary concept list or list of word embeddings into just American English, but then you need to also have a normalization algorithm, or even just a few lines of code that can translate or better replace British English with American English. Then if you want to go one step further, but then if we do this, we are talking more about semantics rather than syntactics. You could also have a dictionary with synonyms like WordNet, for example. But anyway, if you are interested in this, we have a lot of information on the book, like those works that focus on text only, those that work on ASR, automatic speech recognition, and many different data sets that you can use, but also benchmarks that you can use for evaluation. As you can see, many are taken from Twitter or X, and they are focusing on many different downstream tasks. We have used microtext normalization mostly for polarity detection. As you can see here, my Indian PhD student Ranjan Satapathy was the one who did his PhD specifically only on microtext normalization. So every time you see his name here, there's some works that he did, and he also wrote a nice survey paper on this. But anyway, that's all for the microtext normalization module. If you want to know more, you can ask me later, or you can just look at the book, or you also feel free to contact my PhD student. Well, he's no longer my PhD student now. He has graduated and is working at A Star, which is another research institute here in Singapore. Next is SBD, or a sentence boundary disambiguation. This is also a rather simple task because we are still talking about processing text at syntactic level, but very important. Why? Because many algorithms for example, polarity detection, they really work at sentence level. So if you don't have something that can really break up long texts into sentences in a proper way, then you're gonna mess up the whole categorization. And in English, this is fairly simple most of the times because you just have to look for the full stop, for the dots, but not all the times. As you can see in these three examples, sometimes when we are defining time or specifying, like if someone is Mr. Doctor, or they have some initials in their name, or even for some countries like UK and USA, we are using dots. So we need also something to be able to disambiguate these scenarios, and hence define where a sentence starts and where a sentence stops. So despite this being a relatively simple task, it's still quite important, and that's why in the book we also list some of the recent, some not so recent works, even from 1989, but there are also some more recent from 2020, and you can take a look if you are interested in this topic. Post tagging is also very important. POS stands for part of speech, and this is really useful later on for other things that we'll see later, like word sense disambiguation, because English, being a relatively simple language, it uses words in different with different meanings and in different contexts. It's like there's a lot of reuse of words which you don't see in other more complex, for example, European languages. But because of that, then you need something to disambiguate, and we'll talk about a bit more about this when we talk about word sense disambiguation. Post tagging is more about defining whether something is a noun, a verb, or an adjective, and sometimes it can be that the same word is used in different ways with different post tags. And here exactly you can see how the word back can assume different meanings depending on which post tag or how it's used in the sentence. And in sentiment analysis, post tagging is very important. There are a lot of examples where a word doesn't just change meaning, but also polarity with different post tags. Think, for example, of the word fine. Fine as adjective is positive, but as a verb, sorry, as a noun, is negative, like getting a fine. And there are many others of these cases, like pretty. And so here, if you're interested in finding more information about this, you can also look at this post tagging in the book. I think here there's a problem. Yeah, this table is wrong. This is about SBD, so I need to fix that. But the one on the right is correct. And here also we were looking at mostly X or Twitter corpora. But these are correct. Here you find all the different kinds of post tagging methods. Some are using deep learning. some are semi-supervised, and so on. You have a lot of information here also about the data sets. Wall Street Journal is the one that is mostly used for post tagging, and that's pretty much it for post tagging. Text chunking is also relatively easy task where you're basically chunking text or sentences into different parts. This is very similar to post tagging, but it goes one step further. And this is similar to what I discussed yesterday about the fact that most languages have a fixed structure, like you have a noun, verb, and object. So that's what text chunking is doing. And this is important because then sometimes for the subject or even for the object, you can have a very long piece of sentence. Like if I say something like, I bought something from uh, the corner shop that we went to when we were on holiday last year, and blah, blah, blah. All these things that I said after the verb are the noun phrase that come after the verb. And for us, it's very intuitive to understand that that's like the object of the verb, but not so much for an algorithm that doesn't have this sort of training. So it's important with text chunking to sometimes leverage on post tagging to understand better the sentence structure. This can be also useful for dependency parsing, which is also important for polarity detection. And here, once again, you have some tables that show you what are the current methods that are used together with different data sets. Cornell is quite popular. The Conference on Natural Language Learning has provided a lot of data for this specific task. And here you see, once again, how you can do this either by doing feature engineering or by applying deep learning. And here, like especially if you if you download the digital copy of the book, all these are clickable links so that you can go and see the actual work. To conclude, let's talk about lemmatization. This is something also quite important. Why? Because you don't want to have all the inflections of verbs and objects in your dictionary, or again in your word embeddings. This is something that we discussed also 2 days ago when we mentioned different types of word embeddings like fast text from Meta, which took into account all these different inflections. So the takeaway here, the point is what here? For things that represent the same action or the same meaning in general, I would want to have one single concept or one single word embedding or one single representation. So I need to have something like a lemmatizer or a stemmer or something else that can connect or replace all these inflections with the actual uh, word or multi-word expression. So I'm talking about doing things like removing plurals, stop word removal, verb inflections, and so on. But even other things that are not here, like case folding. For example, um, if I have an instance with eat burger with the capital B, I don't want to have a different embedding for that, right? I want to perform case folding on that so that it can also be connected and refer to the most canonical form. And this lemmatization actually is something that is extremely important, and in the past was a bit difficult to do, but now actually it's easier with deep learning. But we also have libraries like NLTK Lemmatizer that can do that for us. But in some cases, it's still okay to just use a stemmer. What is a stemmer? Something like the Porter stemmer just cuts away the last part of words, and so that you only focus on the root word. The problem with this is that while lemma gives you another form that is using English words, when you use a stemmer, you no longer have English words sometimes. Another problem with the stemmer is that in English, again, being a relatively simple language, you have a lot of words that actually mean different things. So in many cases, you can use a stemmer and it can be quite efficient, but you need to be careful of some exceptions. So, for example, one simple and efficient rule is to remove ed from the end of a sentence, right, as a suffix, so that compressed become compressed, and you can only save an embedding for compress in your knowledge base. But the problem is that sometimes in English it doesn't work like that. Stuffed becomes stuff. Er is also a common suffix that I can remove, but then cater become cat. Fasting also ing form. Usually it's a good idea to remove the ing form, but in some cases when you do that you get a different meaning. And here you have many more, like for example the y at the end of a sentence can be usually removed to get to the lemma or root word, but not in some cases like this. Slimy becomes slim, caring become car, and so on and so forth. And here's in the slide, I put some information about how to build your own stemmer if you want. It's about creating some rules so that whenever you find a specific suffix, you replace it with something else. You can potentially do the same also with prefixes. But it's not about which one is better. In fact, for SentiGNet, we use something that is something in between a stemmer and a lemmatizer. If you are interested in this, you can also read the paper Sentic Parser. So this last few slides about lemmatization, I want to clarify that it's not that one is better than the other. If you have no idea what to use, definitely it's safer to use a lemmatizer, which again you can just download from NLTK. But in some cases, like when you want to do maybe document categorization, maybe it's better to use a stemmer, as you can see in this example here. If I have to classify documents as whether they are about uh, Democrats or something else, then using a stemmer is very powerful, because then all these words will be normalized as Democrat. So I just need one word, and everything else that is similar to Democrat will be automatically classified as Democrat. But in other cases, what's the problem with this? The problem with this is that I lost some information. I lost information about the post-tagging, for example, because these were nouns, this is an adjective, and these are verbs. And so if I do lemmatization, I take a safer approach where I remove plurals and I remove inflection of verbs, so that all the verbs are replaced with the infinitive form, but I still preserve the post-tagging. So in general, lemmatization is safer, but it also comes with some problems in general, unless you have a semantic-aware lemmatizer, because then if you have seasoning and season and you replace it with season, then you lose some meaning there. Same with developed and developing. Let's say I'm reading an article about developed countries versus developed country, and then if I do lemmatization, then I don't recognize which country is which anymore, right? And same with other problems like case folding, removing all plurals, and then also plurals removal in general. So again, not just not you can't say that one is better than the other, but it depends on your application and your data. Once again, you have a lot of references here in the book about some benchmark and corpora about lemmatization, some more recent, some not. Of course, this is more about linguistics than computer science, but it's still important if, especially if you want to work on NLU, because then you want to supposedly work on the representation of meaning of what? Of the root words and of the lemmas, not of all the inflections of these. So that concludes the first part, which is the syntactic layer. Are there any questions so far? Are these things that you guys already know that are using? How do you use them? I'm also happy to know all these things. I don't see Vivek today. Where is Vivek? Ah, here he is.
I'm here. Good morning, Arik.
Okay.
So I have one question. Actually, I was quite interested in knowing this part of POS tagging.
Mm-hmm.
So from the syntactic point of view, whenever we study any POS tagging, we generally get phrases, right? A phrase, but sometimes we also have in a syntactic tree some virtual nodes, which can be formed. Like suppose if I say Eric is doing a presentation and I want to form a phrase which is consisting of doing a presentation. So such kind of a syntactic study, is it a part of the syntactic layer or not?
Yeah, again, there's a it's sort of a gray area. In fact, it's not fair to say that what happens at this layer is all syntactic and what happens here is all semantic, because then even here for post tagging, you may need some word disambiguation and vice versa. Here, the idea is that we're trying to do a pre-processing of texts and prepare it for some more advanced classifiers later that are maybe trained on more formal and standard data. A good example for that would be microtext. So here again, I can take two approaches. I can just build a statistical model that is trained on microtext, or I can focus on formal text and then have a microtext normalization tool that kind of translates microtext to formal language. But yeah, there's actually a lot of interoperability between the two layers as well. Some people will also tell you that to do text chunking, you need to understand some semantics of the sentence, for example. So um, it's both ways, and you can also take different approaches to this. You can try to do this in parallel or in a sequence, like steps of normalization. That's up to you. This is just a high level guidelines of how things could be done with particular focus on sentiment analysis.
Okay, and if I have to also do, as my target in my research is to do word order disambiguation also. So where would you place that? If you can also add that thing in your talk, that will help me to kind of develop insight about it.
You said word order disambiguation. Did you mean word sense disambiguation?
I guess these are different things, but by word order disambiguation, I mean there is a principle called as scrambling. Language like
Mm.
Hindi or Japanese, they allow scrambling a lot. So if I have to deal with such a problem, how can I work on upon that?
I never had to do anything like that. I guess you could have a model that tries to find some sort of similarity between the new sentence where word order is scrambled and some other structure that are similar in your training data. But yeah, this once again, this is more meant for standard languages where you have a specific sentence structure. But the problem, yeah, the problem is that when you scramble words like you do normally in a bag of word model, you it's very difficult to then do post tagging, for example. That's where you really need to disambiguate, and most tools use for example, deep learning to understand the context of a sentence, and based on that, decide what is the sense to choose, what is the post tag to choose. If you don't have that luxury, then you have to resort to intuition. So it's going to be more about um, words that appear together in the same sentence rather than not, if you don't have the luxury to look at the sentence structure and the sequence of words. But that's just an educated guess. I never worked on that problem before.
Okay, okay. So I'm actually looking forward to this word sense disambiguation to understand that.
Yeah, I mean, I'm just gonna have a few slides on it, but if you are interested, you can look at the book or we can discuss more. We have a very interesting work from last year that does word sense disambiguation in an interpretable manner. So if you are interested, I can also send you that work.
I would love to read that.
Actually, we also embedded that work on Syntactics 8. So if you look at the paper Syntactics 8, which is available online, you should also find that algorithm for interpretable word sense disambiguation. But again, if you cannot find it, you can send me an email and I'll send you the paper.
Sure, I will read it, appreciate it. Thank you.
No problem. Um, so should I proceed? Do you guys want to take a break? Or you guys want to do? Maybe I'll do one module, word sense disambiguation, and then we can take a break. Because again, by today I want to finish the whole module, so we need to do maybe half of these modules first. So the next layer is more about semantics. So supposedly after you've taken care of the syntactic parts, you want to start doing more semantic aware um, labeling or processing in general. But semantics is also a very ambiguous word because then different people working on different contexts, they call semantics in a different ways. Cognitive psychologists call semantics and like in terms of like frame semantics, understanding situations. It's more similar to situational and intentional awareness. Linguists, for linguists, semantics are one thing, and for us computer scientists another. But in general, semantics is when you are trying to work with senses and meanings rather than just looking at syntactic properties. Here in the book, we have a lot of examples with different downstream tasks. uh, Again, our focus maybe is polarity detection, but we also experiment with others. And here there are some examples of which of these models can be used for which downstream tasks. Are they mutually exclusive? No. In fact, for polarity detection, name entity recognition is also extremely important to find name entities in text and have better polarity detection. But this is just indicative based on the papers that we reviewed and the paper that are in the book. So once again, it's just to give you a snapshot of what can be done with these models and what kind of downstream tasks they can be applied to. So word sense disambiguation is about what? It's about the fact that in English you have the same word meaning different things. You also have this in other languages, but um, very much many more in English than other languages. And in some cases, like maybe these examples in this picture are not really the best because these actually are um, they're actually pronounced differently. right? Moped, moped, bow, bow, entrance, entrance, minute, minute. So tear, tear. So in this case, these are very specific word sense ambiguities that only happen in text, because in speech you don't have that problem. It's just that these words just happen to be written in the same way. But there are many other words that are written and pronounced the same way and they are ambiguous, or like I mentioned before, right and right, which are that sound the same but they are written um, differently. So the main point here is that for us, doing word sense disambiguation is something that comes extremely natural, because we can always tell which of these word is which based on the context of the conversation. But it's not so trivial for an algorithm. So this actually has been a very problematic issue for many years before deep learning came about, because now with deep learning is relatively easier to do word sense disambiguation. But in general, in the past, there were two main approaches. One was knowledge based and one was supervised. And this was mostly looking at conditional probabilities, like if you, for example, have the word bank, which is one of those examples that is pronounced and written similarly but have different senses, then you always look for other words that can link the word bank to the institution or maybe the bank of a river. So here, once again, I don't have, we don't have much time to go into the details, but in the book, it's thoroughly explained what is word sense disambiguation and what are the main issues and the main algorithms, and also data sets. Semeval and Senseval have provided a lot of very useful label datasets for word sense disambiguation in the past. And here you also have different approaches. Some are knowledge based, some are supervised, and there are some interesting ones that could be considered neurosymbolic, because they use a bit of both. They use a bit of knowledge representation, but also statistical analysis. So that's it for word sense disambiguation, and I think it's we should take a break because we already talked for 1 hour. So let's uh, let's meet later. If you guys have any questions, maybe you can ask me after the break. So let's meet again in half an hour.